Our first segment we're going to look at today is called the median of a triangle. A median of a triangle is a segment that connects a vertex to the opposite midpoint. Of a triangle. So we're going to connect a vertex down to the opposite midpoint. If you like a picture that there's a nice diagram here in the box below. Notice in each of these we connect a vertex to the opposite midpoint. These blue lines are each medians. This guy from B down to F, notice F is the midpoint. We connect the vertex down to get a median. Connect vertex to midpoint D, get a median. These are called medians. Also, it's hopefully not a secret, since I put this diagram in, that the medians of a triangle are concurrent, meaning they all intersect. That point of concurrency is called a centroid. The point of concurrency of the medians. Of a triangle. Okay. That point where the three medians intersect, like on our diagram here, is called the centroid. In the diagram below, P is the centroid of this triangle. The centroid theorem describes kind of where the centroid is located in a triangle. The centroid of a triangle is located at the following location. It is located two-thirds of the way from the vertex to the opposite point. Two-thirds. Which means it breaks since it's located in each median, it breaks each median into two chunks. A two-thirds, one-third relationship. Now what's nice is, how are two-thirds and one-third related to each other? How would you compare those two distances to just the two-third chunk and the one-third chunk?
Two-third chunk would be could be twice as much as the one-third chunk.
The two-thirds chunk is twice as big as the one-third chunk. So what we're doing is breaking each median into two segments. One that's twice as long as the other. So for example, since P is the centroid of this triangle, this segment PF is half as long as PB, or BP. Because this is two-thirds of the entire segment. This is therefore one-third of the entire segment. And if you compare two-thirds to one-third, this is twice as much as the one-third segment. And it does that with each of these. Also note that this theorem does not describe any relationship amongst the three medians. This theorem says nothing about how one median is related to another median. All it says is something about the lengths of one median given the centroid. An easy trap to fall into would be to say that this segment, AE, is the same length, or say congruent to, how about CD?
We only know that
An easy thing to do, an easy trap to fall into is say, oh, well, they're medians, so they're congruent. Because that's the centroid theorem or something. And that is totally false. This theorem, the centroid theorem, says nothing about the medians compared to each other. All it says is that any given median, the centroid breaks into a 2/3, 1/3 chunk. Okay.
would have to be equilateral.
We'll actually see. We'll see eventually that an equilateral triangle has some really nice properties. In fact, the median is the same as perpendicular bisector, same as an angle bisector, same as an altitude. We'll get to in a second. They're all like the same thing if it's an equilateral triangle. So I'm going to give you a triangle and give you some information about the triangle. First of all, I'm going to tell you that G is the centroid of this triangle ABC. Also, I'm going to tell you that segment AD has a length of 8. Tell you that AG, from A to G, has a length of 10. And that the length of segment CD happens to have a length of 18. Let's find some missing distances. What's the length of B? What does the length of BD have to be? Someone says 8. Why 8?
Because D is the midpoint of AB.
Since G is a centroid, that means it's on the segment that connects the vertex to the opposite side at the midpoint. Therefore, those two segments are the same length. Therefore, BD is also 8. G is the centroid. Where is the centroid located? It's on the median. What's a median do? To the opposite midpoint. So therefore, D must be a midpoint. Since G is a centroid, D must, since on the same line, D's got to be the midpoint. So therefore, these segments are congruent. You could also claim that since G is on these other two segments, they're also medians, which means if you wanted to claim, you could go through and say that all those segments have to be congruent. Okay. All right, next. What's the length of AE? What's the length of this segment? Okay, Steve?
5.
AE is most certainly not 5. It's 15. Okay, what segment is 5? GE is certainly 5. Why is it 5? Well, we just got done saying, since G is a centroid, then it's 2/3 of the way to the other side. Or we also noticed that the two segments created, the longer segment's twice as long as the shorter segment. So if this guy's 10, then its shorter segment must be 5. And then the segment addition postulate says that this thing's got to be 15. For sure. What's the length of CG? What's the length of this segment?
12.
12. How do we get 12? Paige?
It's 2/3 of 18.
Okay, so you can take 18 and multiply it by 2/3. That'll give you 36 over 3, which is 12, for sure. What's another way to calculate that segment must be 12? Isabel, what's another way to calculate that?
You could divide it by 3 and add that. Yeah.
And then since this segment's in thirds now, 6 plus 6 plus 6 is 18, and 2 of those is 2/3, yeah. So it's just another way to calculate 12. You'll see some more questions like this in your homework tonight. I'll give you a triangle, tell you you've got a centroid here, then we'll do some 2/3, 1/3, half, and twice as big calculations. So our altitudes of a triangle is defined as the following. An altitude simply is a segment. Is simply a segment that connects a vertex of a triangle to its opposite side or side extended at a right angle. The main reason why we're looking at altitudes is that in altitude we're going to use a lot to find what's called the height of a triangle. Notice that a segment going from a point to a segment at a right angle defines the distance between a point and a side. We can find the altitude. We're finding a quantity of a triangle called the height of the triangle, which we'll use a lot to find, say, the area of a triangle. Since you're going at a right angle, you could use this. This could help aid in finding, say, the lengths of a sides of a triangle, because now you can use Pythagorean theorem because you create right triangles. Altitudes are pretty important segments that we're going to use going forward. Okay. So let's create some. How about we draw one in? Find the altitudes of each of the triangles coming from the uppermost angle. So here's my uppermost angle. I'm going to draw an altitude or connect this point to this side at a right angle. Point, side, at a right angle. Altitude. This segment would be the altitude of this triangle. If I want to draw the altitude for my second triangle, this obtuse triangle, I need to connect this point to this side at a right angle. Yeah, notice that I can't just connect it over here. That won't go at a right angle. So this is an example where I need to use what's called the side extended. So I'm going to extend my side of this triangle out, and now I can draw the altitude. Notice that when I draw these uppermost altitudes, the line is dropping down to the side. A lot of time it's pretty common to say drawing an altitude is called dropping an altitude down to the other side. Dropping an altitude is a pretty common way to call drawing.
Could this help you find area?
This definitely will help you find the area of a triangle, because the area formula is base times height, and the height is measured at a perpendicular distance. So if we can find the length of length of an altitude, then we can find the height of a triangle, or the area of a triangle. I don't know why I did this. I'm going to skip down to the bottom here. This thing called the orthocenter theorem, it's more or less a definition. The orthocenter theorem says the following. The altitudes of a triangle are concurrent and meet at a point called the orthocenter. They're kind of these weird triangles, like these obtuse triangles. We can actually find an orthocenter of this by extending the sides and drawing in the altitudes. it may or may not, the orthocenter may or may not even be anywhere close to the triangle. So for example, for this one, if I want to draw an orthocenter, that means I have to draw the altitudes, and I may have to extend them pretty far. Like for example, if I draw in, what if I draw in the 3 altitudes of this triangle? So if I draw the 3 altitudes of my little triangle here, I got 1, I got 2, and then I may have to extend this side a little bit. And I'll draw the 3 altitudes of a triangle. The orthocenter theorem, all it says is that they actually do intersect. And where does it look like they're going to intersect?
Down there.
Like way down here. And we actually show that they do. If I just extend them way down. All I'm doing is extending these. Hopefully. Yeah, look at that. They intersected. Yeah. Yeah. So if you extend the altitudes of triangles, they intersect, and they intersect at a point called the orthocenter. For an obtuse triangle, the orthocenter is outside of the original triangle. For a right triangle, the orthocenter has to be on the side of the triangle. It's specifically at the right angle vertex. And, well, actually, not necessarily there. For a right triangle, the orthocenter can be, I think it's on the side, actually. And for a acute triangle, it's inside, for sure.
Can you put the definition up for this?
This is the definition, or the orthocenter theorem. All it says is they actually do intersect. Okay. In order to do my nice example 3, I have to erase my orthocenter drawing. Okay. Last but not least, we have this example. And then I'm going to give you a generic looking triangle, A, B, C, D. And I'm going to draw a segment in. I'm going to give you some information about the triangle now. And we're going to decide what of those 4 parts, of those 4 created segments that we've had so far, perpendicular bisector, angle bisector, altitude, or median, which one of those is our drawn-in segment forced to become, based on the information we're given? We'll start with this first guy. What if AD is just perpendicular to BC? What if all we know about this segment is that there's a right angle there? What kind of segment is segment AD forced to become? Is it necessarily a perpendicular bisector? Well, what is a perpendicular bisector? What would we need to know? Kelsey? It's definitely intersect at a right angle. What else does it need to be a perpendicular bisector? Yeah, we need to know this is a midpoint as well. And we don't necessarily know that. How about an angle bisector? Can we claim this is an angle bisector? No, not really. We don't know anything about the angles, and I don't know much more. Is it a median? Well, it can't be a median. We already said that we don't know that these are the midpoint. This is a midpoint, so it can't possibly be a median. Is it an altitude? Yeah, it certainly is. It goes from vertex to opposite side at right angle. Just knowing this, all we know is that AD is an altitude. Is the only thing we can claim, unfortunately. What if we toss in an additional piece of information? What if on top of knowing it's a right angle, we also know that segment AB is here into segment AC? Does this tell us really much, if anything, more? Does that force AD to be anything else? Joel?
Yeah, well, I think when you know that, then you know,
It's certainly altitude, but what else do we know?
I was gonna gonna say now that since you know that, you can figure out the triangles are equal to each other, or you can do
Congruent to each other.
yeah, congruent to each other.
Okay.
You can do hypotenuse like.
Okay. So what does that tell us? If we know that triangles are not
AB
congruent.
equals DC, so that means it's a perpendicular bisector.
So since you could definitely explain, as Joel said, you could definitely explain now that you have hypotenuse leg congruency of this triangle. So we certainly know that these two now must be the same length. So we definitely know that it's a perpendicular bisector. What else does it say?
Well, could we know that it's a perpendicular bisector before we have it? They're congruent because the converse of the bisector theorem says that if they're congruent, they both.
Yeah, you didn't even need to know those are midpoints. Just knowing these, the perpendicular bisector converse tells that yes, that this must be on the perpendicular bisector. So it's definitely a perpendicular bisector. Absolutely. Is there anything else? Is it forced me anything else now? Paige?
Maybe an angular bisector?
Why?
Because we know that
We just, how about Joel's reason? That we have congruent triangles. Congruent, corresponding parts of congruent triangles are congruent? Sure. That means that's definitely an angle bisector, for sure. Because with congruent triangles, you can use CPCTC. Definitely angle bisector. Is it anything else? Is it a median? What is a median?
It's a line that goes from the vertex to the midpoint.
It's a line that goes from a vertex to a midpoint. Is AD a median?
Yeah.
Yeah, absolutely. It goes from a vertex to a midpoint. Therefore, it's also a median. By adding one piece of information, by knowing one extra thing, we can go from knowing that AD is forced to only be an altitude to being forced to all four of those specific segments. By knowing one piece. A big part of your homework tonight and of the chapter test we'll take at the end of the week is going to be looking at a diagram and giving you a little bit of information and being able to decide what one of those, or maybe more of those special segments that we've been creating throughout this chapter, what is it forced to become? Okay? In this case, that's an example where it becomes all four.